Alright, we've arrived. Final video of our calculus journey and our integration exploration will be on integration by substitution, but just a quick recap as to the purposes of integration. Remember, integration allows us, it's a process of finding signed area. Right, so that's through definite intervals. And then it also doubles as the process of finding antiderivatives, which is through indefinite intervals. And obviously our fundamental theorem, parts 1 and 2. But the purposes of this one. So most of the functions that we're working with, aside from our trigonometric functions, have relied on the power, reverse engineering the power rule for derivatives and applying it to integration. But we also had instances when we took derivatives of things that were a product rule, or a quotient rule, or a chain rule. So we're going to learn this technique now, but when you journey into Calculus 2, you'll learn a few other techniques to assist you when your integrand becomes a little bit more complex. So if capital F prime of x is equal to the original function, then the integral of f of u of x, so this is really the reverse chain rule, is equal to, f of ux times u prime of x dx is equal to f of u of x, let's see, right, so the antiderivative composed with that inner function. Okay, so essentially what we want to do is we need to identify almost, visually that a chain rule exists with the functions that we've been given, or we need to be able to create a chain rule within our integrand. That way we can just apply the antiderivative. So take, for instance, something like this. 2x cosine of x squared dx. We have cosine, we have x squared, and we have 2x. I have an outer, an inner, and then a derivative of the inner function. Okay. It is apparent that this x squared will operate as my inner function, and 2x will operate as the derivative of the inner function. So I really can just rewrite this as sine of x squared plus c. Because if I derive the antiderivative, I get cosine of x squared times the derivative of the inside, which will yield a 2x. So typically, what we do and this is once again a contrived example that's supposed to work out very neatly, is select the appropriate function for u of x. And what do I mean by that? I mean this. So if we have f of u of x times u prime of x dx, that this is equivalent to f of u, and this piece here becomes du. So where du is equal to u prime of x dx, so that I can rewrite the integral as the integral of f of u du, and then I can most likely apply some type of power rule, or maybe I have a constant function altogether. But let's get away from all of this notation, and let's do what we do best, which is practice. So let's say I have this function. Okay. Well, yes, you could expand that to the 5th power and then reverse engineer the power rule for integration. We can choose x squared plus 9 to be u and du to equal 2x dx. Okay. However, we can see that all we have is an x dx. So if we divide, because it's an equation, by 2, du divided by 2 is equal to x dx. So for these two terms, I'm going to substitute in a du divided by 2, and for x squared plus 9, I'm going to substitute in a u to the 5th power, and now I have this f of u du. And I can integrate this, right? This is power rule. I can remove the constant to outside of the integral, and this becomes 1/2 u to the 6th plus c, u to the 6th divided by 6 plus c, and I would just want to make sure that I remember to resubstitute in x squared plus 9 to the 6th over 12 plus c, and that is the integral of x times x squared plus 9 to the 5th. Okay. It works out quite nicely when we have algebraic functions. So what I'm going to do is do one on and one off. If you have this rational function, x cubed plus 3x squared plus 12 to the 6th, you will come to realize that the final answer is something like this. And it's up to you to figure out how to get there. Now let's delve into the lovely world of trigonometry. So right now, there is no singular trigonometric term that when we derive it, we'll get a tangent of theta. So typically, more often than not, when we have the tangent function, we want to do a rewrite of sine theta divided by cosine of theta d theta. Now remember, we want to select a function such that the derivative of that function will be remaining. Okay? If I select u to be cosine of theta, du becomes sine, negative sine theta, d theta, which notice exists here aside from the negative sign, so we can just move it over. And now our inner function becomes negative 1 over u du. And you should remember from earlier in this unit that when we have this type of rational function, we really have the natural log of u plus c, and a quick resubstitution leaves us at our final derivative. I'm going to do one remaining problem and leave you with 2 to conclude our video. For my Rutgers students, we can pick up with this on Friday to ensure that you've done it correctly. If you're not my Rutgers student and you're just a random person watching this video, comment and I'll let you know if you did it right. Let's say we get something like this. X root of 5x plus 1 dx. Okay. Anytime you have weird symbols that are going to lead to weird exponents, that's what you're going to want to set u equal to. Bringing in constants because they will derive to 0. So if we derive this, we get du equals 5, which doesn't really do much for us, okay? Because there's still an x remaining here. However, if we rewrite this in terms of x, I can now substitute that in. And dx would be equal to du divided by 5. So this integral becomes u minus 1 divided by 5, which represents x, times u to the 1/2 times du divided by 5. Okay. And yes, while it does look pretty scary with all this mumbo jumbo going on, we can pull out this constant of 1/25 while distributing this u to the 1/2. And we really wind up just integrating u to the 3/2 minus u to the 1/2 du. This is just power rule. Okay. This is the beauty of substitution. It just turns, typically, if we make the right call on what function to substitute, it vanquishes everything. So we get 1/25 times, if we're going to add 1/5, so the reciprocal of that, as such, minus 2/3 u to the 3/2 plus c. And then we would just want to make sure that we resubstituted in this expression. So yes, our final expression looks absolutely hideous. However, the actual integration is not remotely bad. Okay, so let me leave you with 2 for u. And like I said, for my Rutgers students, we can pick this up together in class. Alright, and without further ado, it's been a pleasure. I hope you've walked away with a little bit more knowledge than what you began with. And if you have any comments or feedback, I'd love to hear it. Let me know.